Quantum physics explains the nature and behavior of subatomic particles. Much like how psychology explains why little kids behave a certain way, or the probability that they could grow up to be a certain way. Quantum physics is mind-blowing, controversial, and pretty complicated. But let's break it down. Wave-particle duality is a complex and fundamental concept in quantum physics. It states that elementary particles may be described not only of particles, but also of waves. To illustrate wave-particle duality, we will be using balls to represent subatomic particles. If you took a slingshot and shot many balls through a board with two holes, the balls would either enter the hole and hit the observing screen, or it would hit the board and bounce back. However, this is not the case. You soon realize that there are bands of different widths of balls formed on the observing screen. This is called the interference pattern, which can only be formed by a wave. So what is happening here? Imagine this. When you throw the ball, it goes through an invisible machine which transforms the ball into a wave. This wave actually passes through both slits and form an interference pattern. When the wave hits the observing screen, the peaks and troughs of the wave create what we see on the observing screen. To make things weirder, if you had someone else stand at the board and observe which slit the ball passes through, the ball actually behaves like a particle and two bands of balls are formed on the screen instead. It's almost as if subatomic particles are naughty kids who only behave when we observe them. How could this be? How could a mere act of observation or measurement cause the particle to behave differently? This indicates that without observation, reality doesn't exist. Particles would just exist as the wave of probability, something that could or could not exist. Quantum entanglement is still a mystery to many physicists. It occurs when pairs or groups of particles are generated or interact in ways such that the quantum state of each particle cannot be described independently of the others, even when the particles are separated by a large distance. To illustrate this, imagine we have two Earths representing subatomic particles, one spinning clockwise and the other spinning anticlockwise. We don't know which Earth is spinning clockwise and which is spinning anticlockwise, but we do know that their spins are opposite. Now, let's put one Earth in another galaxy and one Earth in another universe. Quantum entanglement suggests that when we observe or measure the spin of one of the Earths to be clockwise, we actually force the other Earth, or the other Earth even chooses to be opposite spin. How do these two Earths communicate? Nothing goes faster than the speed of light. So how is it that the two Earths can send messages to each other faster than the speed of light? Einstein called this spooky action at a distance, and he believed that there was information stored in the particle before you measure it. Thus, no message would need it to be transmitted quicker than the speed of light. Of course, there are many interpretations of quantum entanglement, but no one knows for sure which interpretation is right. Perhaps this is a love story better left unexplained. The quantum world has opened up many possibilities, such as the theory of parallel universes, quantum teleportation, quantum computers, and so much more. Give quantum physics a chance, and you may never see the world the same again.